I'm Michael Greminger. I'm an associate professor in the Mechanical and Industrial Engineering Department at the University of Minnesota Duluth. And today I'm going to talk about a project where we're using generative adversarial networks for enforcing manufacturing constraints on topology optimization. So this is our network structure, and I'll zoom in a second here so we can actually see what's going on. But like I said, we're using what's called the multi-scale gradient GAN. I'll talk about what that means in a second. But with a GAN, there's two major components. One is called the generator. The generator is what generates those new images. So when you saw those images of the flowers or faces, it's a generator that's creating those two images. What we're doing is we're extending this beyond 2D and just doing the next step and extending it to 3D. And then you have what's called a discriminator. And so what you have during the training is this competition between the discriminator and the generator. So the discriminator takes the images as input and outputs a classification. Does it think it's real? In this case, greater than 0 indicates real, less than 0 indicates fake for the hinge loss function that we're using here. But in general, it's telling us whether the image is real or fake. And so what happens is during training, the generator generates fake images. The discriminator is shown both fake and real, and it's rewarded for correctly classifying fake and real. And the generator's rewarded by the cost function for tricking the discriminator. So you have this training that alternates between the training the generator and training the discriminator. And if it works properly, as it converges, you get a generator that creates images that are more and more realistic. So we're applying that to generating 3D models instead of images. So we'll train it with parts that are manufactured with a very specific manufacturing process to train that GAN. One key thing on the GAN is that you're feeding it a latent vector, so a latent feature vector, and you're generating these at random during training. But when we do the topology optimization, these are our feature vectors. So as each of these latent vectors results in a different image. So in the face example, each latent vector would result in a different face. All of them would be faces that don't exist. And so in our case, these feature vectors generate each in their 128 feature elements long. This feature vector generates a unique design. A training data needs to be generated to train the GAN. So again, in order to train a GAN successfully, you need a lot of example images, usually tens of thousands or more, that are training successfully. And so for the case of these manufacturing examples, we often don't have that many examples of parts for a particular manufacturing process in order to train the GAN. So what we're doing is we're going to generate those models synthetically. So this next slide just shows 3 examples of the training data. They'll all be manufacturable with a 3-axis machining operation. So it's showing, and we have 20,000 of these data points. So these are just 20 randomly chosen models from the GAN output. Now some of them you can see could be pretty easily manufactured with a 3-axis CNC. Some of them have some additional artifacts of features. Now if you trained it longer, these would probably get more and more like the training data, but we stopped it at this point. We see even at this level of training, we're going to get some pretty good results when we apply this topology optimization. So we're going to use, this is just showing the traditional topology optimization, nothing new here, this is just kind of your straightforward compliance minimization optimization problem. So we have our compliance equation, we have a target volume fraction, we use 0.4 for all the examples here. We're optimizing it by setting the element densities between 0 and 1, and then use this finite element model to calculate the displacement from the element densities. To calculate elastic modules for each element from element densities, we use the SIMP model, and this just helps to force those densities between 0 and 1, and we use the power of 3 in that equation. And then we have the compliance gradient. This allows us to update the element densities for each iteration, and this is just the standard compliance gradient. To adapt this to GAN, the main difference here is we're now not optimizing on element densities. We need to calculate element densities based on the generator. So G is our generator, our neural network generator. Z is that latent vector I showed you before. Now, so this is a much lower dimensional space, whereas we had to optimize on every voxel. Here we're only optimizing on 128 input vector, Z, but we need to convert that into element densities. So here we use a neural network directly. Now, the neural network kind of naturally generates values at 0 and 1, so we don't really need to use the SIMP model, so we don't use that here. We get the modulus directly just by multiplying the output of the generator by this E naught. And in here, we just update our gradient function. We just use the chain rule for multiple dimensions. We need to get the gradient through our neural network of the latent vector to the element densities. And here we're using PyTorch as our neural network algorithm, and that has an automatic differentiation capability, so we use that to calculate that gradient. So I'll show a couple load cases to see how well this works. So this is load case 1, just a simple boundary condition with a force. Here's a traditional topology optimization, and here's our GAN-based topology optimization. Our volume target is 0.4. So the best way to show this is just show you a 3D view of this model. So here we can see the traditional topology optimization, and you can see that this design could not be manufactured with a one setup on a 3-axis CNC machine. You can machine it from this direction, but you're not going to be able to get some of the material removed here. And I'll illustrate that a little easier. I'll just show you the voxels you can't reach. These red voxels would be what should be removed, but can't be removed by a one setup 3-axis machining. And what I did was look from each of the 6 sides, find the direction that had the least unreachable voxels, and that's shown here. Now, if I look at the model we got from the GAN, so here, GAN load for that same load case, you end up with this totally different looking model. But this model can now be machined through 3-axis machining. It turns out the direction you machine it from is from this back side. And if I show you the unreachable voxels, there's still a few you can't get to, mainly due to noise, but it's very few, and you can machine most of those voxels. So now we go from a design that wasn't manufacturable on a 3-axis milling machine to one that is. It looks dramatically different, but we'll see the compliance is almost identical to what we had with the traditional topology optimization. We can kind of quantify these results and show that here's the compliance. So traditional and GAN for load case 1, the compliance doesn't go up that much. So the lower the compliance, the stiffer the structure. So it's pretty similar. Actually, we're not facing too much penalty. Again, these are both have a volume target of 0.4, so they're the same volume. But what's really different between the two cases is the fraction of unmachinable voxels. So these are the ones that couldn't be reached on a single setup on a 3-axis milling machine. I showed that for case 1. And so for the traditional topology, that's actually 18% of the voids can't be removed. So you end up with more mass. And whereas with the GAN, you only have 4%. So like looking at future work, we need to find ways to speed up this training. 23 days is not acceptable. And we also could use conditional GAN to train one generator to do multiple manufacturing methods. So the input to the generator could tell it, is it machining? Is it injection molding? Is it a different process? All right, thanks for your time.